Hi, my name is Afsi Moveni. I'm an application engineer here at Keysight working on the FieldFox product. Today we're going to be looking at the FieldFox and the noise figure uncertainty calculator. What I'm going to be showing you is use of the uncertainty calculator in Excel, the one you run on your computer, and also the version we have in FieldFox, the built-in uncertainty calculator. If I show you the setup I have here, I have an amplifier that I'm going to be testing the noise figure of. This is actually a Keysight preamp we sell, but here I'm treating it as my DUT. So the setup is I have a noise source that's biased with a 28 volt DC. FieldFoxes have a built-in power supply. So this 28 volts on and off is going to my noise source. This is a Keysight 346 KO1 noise source. The output of the noise source goes to my amplifier or my DUT, and then from there it hooks up to FieldFox's port 2, which is the port 2 SA receiver or for the noise figure measurement. And I've set it up to measure noise figure and gain, and I'll be looking at the uncertainty here on the FieldFox and also again doing the analysis on the computer. So with that, we'll go ahead and we'll start with the Excel, which is the tool I think a lot of people will be using. This is the FieldFox uncertainty calculator, and you actually can download this from the web. If you go to the web and search for Keysight noise figure or go to this URL, there's uncertainty calculators for PNA, FieldFox, and other signal analyzers. I'm running the one for FieldFox specifically. When you bring up this uncertainty calculator, we're going to be exploring it in order. I'm just going to go through the various steps and tie them into the FieldFox measurements. So the first step is the model. What is the FieldFox model you're using? Some of you already have a model, so you can just pick either you have the N99 1X or 3X or the 5X or 6X. The FieldFox models come in two major hardware versions, not counting the ones that came out very early on. Currently, the ones that are 3.5 millimeter type N connectors, these are the 1X or 3X, or the ones that have 2.4 millimeter. But some of you may be trying to decide which one do I want to buy to make a noise figure uncertainty calculator. And there you can either bring up the data sheet and look at the noise figure and search for noise figure, and you can go down in here and read the noise figure parameters listed for the models. Or here, let's say you have N99 5X selected, which is the instrument I'm controlling. I can come in System Information and say FieldFox noise figure. And it's displaying the noise figure here. Let's say the max is about roughly 25, 26 dB up to 20 gigahertz. That's the frequency I've listed. Or I can switch it to the 1X model, and you can see the max is now higher. It's around 30, 32 dB. So you can just switch back and forth and see. And I have in the background a set of data loaded already for a DUT, but I kind of want to show you what happens if you pick different models. So if I have the 1X, there's an impact on jitter. And look at kind of the jitter. This is the total uncertainty you're looking at, a summary. And jitter is this purple line. This lowest line is jitter. And it's somewhere in the 0.05 dB range, I would say. Maybe the highest is around 0.08 dB. Now if I switch this to N99 5X, you can see it got a little bit less. The highest is maybe now 0.06 because we know the 5X models and the 6X models have better noise figure, lower jitter. So I'm just trying to point out the impact you see of these, you would see it on the jitter. But if you're actually using the box, if you're doing the uncertainty calculator on the instrument, it's just one instrument. There is no selection there. The second choice is what's your DUT type. I have an amplifier, linear amplifier. You could also have a frequency converting device. And really the main impact here is what you put for the input and output frequencies, and those frequencies are used in the various calculations. But here we have an amplifier. The next item you pick is the measurement bandwidth, or this is the res bandwidth on the instrument. The default is 5 megahertz. I know a lot of instruments have 4 megahertz. Keysight FieldFox is 5 megahertz. And here really we default to the widest. If you look at FieldFox, this is the noise figure mode. You press the number 2 key, which is bandwidth, you get res bandwidth, and you default to 5 megahertz, but you have a choice of 4 different filters. You want to pick a bandwidth that's similar to your DUT, and unlike traditional measurements, the lower your res bandwidth, the lower the noise floor, the better the measurement uncertainty. That's not quite true in noise figure. And an intuitive explanation for that may be that when you have a wider bandwidth, you have more noise, which makes it a little bit easier to actually measure the noise because you're making noise measurements above the noise floor. So you have a higher signal level, so it makes a slightly better measurement. If you want to read a detailed explanation of this, there's a great discussion on Keysight forum, and you can see the URL on the web. The first part is somebody is answering the question of res bandwidth selection with intuitive explanation. The next person who's answered is Joe Gorin. He's our noise figure expert and co-author on some of our app notes here. So you can read kind of a more technical explanation of how you select a res bandwidth. And he has a recommendation that using a res bandwidth that's similar to the DUT bandwidth as a good trade-off. But I want to show you what happens if you select it. For the settings, again, I have. These are very specific to your case. What happens if you pick a different res bandwidth? I have 5 megahertz. And again, here I'm looking at my jitter, which is this purple line, which is really around 0.06 dB or 0.02 even. So if I now come and change my res bandwidth to 1 megahertz, you can see that it went up from about 0.02, 0.03 to now 0.06. So you can see the impact on jitter. I'll later show you can do the same thing on the FieldFox. You can change the bandwidth, and when the uncertainty bars are displayed, you will see a change because of it. But again, the default is 5 meg. We're going to leave it at 5 meg here. The next is the compression bandwidth. This is the bandwidth where the DUT has gain. If you hover over these eyes, you get information. I am testing this DUT from 1 to 21 gigahertz, so I've left that at 20 gigahertz. It has gain over that whole range. The next setting is frequency. Again, I'm testing this DUT from 1 to 21 gigahertz. It's a little bit more broadband, but I wanted the points to be even just for simpler demo purposes. So I'm doing 1 to 21 gig, and I have 21 points. That's what I've selected. Next, we move over to user cal integration. You do a user cal when you have a preamp. I don't have a preamp in this case. You also do it if you want accurate gain calculations, but I'm again looking at noise figure and I don't have a preamp. So these settings don't apply in my case. I can change these numbers to whatever I want and it has no impact on my measurement because I'm not performing a user cal. Oh, and I want to take a minute here saying this video, I'm not going to go into the details of when you do a cal, when you don't, the explanation behind all of this. There is a great app note. There's a couple. One is here on noise figure measurement accuracy. This is a main one that goes into when you calibrate, the meaning behind all these calibrations, the uncertainty, the math, and so forth. That this is explained here. So that one is really a very good app note, a lot of detail, 45 pages. Another document is a white paper on selecting a Rayleigh distribution for mismatch uncertainty. So there's a couple of papers that are the background behind the app note, with the main one being this noise figure accuracy app note that give you kind of when you want to do a cal, when you don't want to do a cal, and so forth. Now we go into measurement integration time. This is related to your jitter again. How long do you want the box to keep making measurements to be able to reach your jitter goal? And I'll show you on the box. If here you go to measurement setup, integration, and it doesn't take, for example, 1 second if you say 1 second. It'll go up to 1 second to reach half a dB. If it gets done sooner, it exits. You can make it the time really long to get a better jitter measurement. And you can see the impact here, for example. I'm going to look at the jitter, which is this small line here. Okay. Let me make this 0.01 second. I'm going to say I'm not willing to wait very long. And you can see that the jitter got higher. You see that value went up? But if I'm willing to even wait 1 second, then you can see that the jitter got reduced. So you can see the impact of that. Again, you can see this on the box too. So let's take a look at the DUT. So the DUT values can be spot entered. You want the gain, noise figure, input reflection coefficient, output, VSWR. Or you can enter them user entered. We're going to do user entered in this case. But just I wanted to point out that really, at least in this revision of the spreadsheet, which is 1.104, we are not using the output VSWR component. We are accounting for in the uncertainty is the input reflection coefficient of the DUT times the noise source, VSWR. So this one really doesn't matter. And in fact, if I display mismatch here in the drop-down, mismatch is this purple line, which most of my uncertainty is my purple line here. I'm just going to go ahead and change. I'm going to change the output VSWR, for example. I don't know, I'm going to make it 0 just to change it. And you can see it doesn't make a difference. This number is not used in the math. But the output reflection coefficient is. So if I make this, for example, a lot worse, this is 0.25 dB. If I make this 0.8, you can see now it's 1 dB. So this one is, in fact, used. It didn't change that much because the noise sources have really, really good match, so the net mismatch effect is not that high. So, but we are going to do user entered. And when you do user entered, the data comes from this tab called DUT. So we go to the DUT tab. And here you enter the frequency, the units of the frequency, the gain, noise figure, input reflection coefficient, and again, the output reflection coefficient doesn't matter. And you can enter up to 101 points, 106 because it starts off at a higher row. And the way I get these values is I actually got them from my FieldFox. If you come to your FieldFox, you can go into your network analyzer mode. This is without your noise source being connected. Just do a VNA measurement. And this is a little trick. If you set up your VNA as 2 traces, so it's a dual trace view, the order doesn't matter, but I've set the top as S21, which is the same as my gain, and the lower one is S11, which is my reflection coefficient. And I've got my S21, my top traces in log mag format, and I've got my S11, which is my lower trace, in linear format. And I did that because when I save this file in CSV, it saves it as the format I'm displaying it. And then I can use this data, copy and paste it into my Excel spreadsheet. Because here the gain, it's expecting it in dB and is taking the input reflection coefficient as row or linear. So it just makes it easier if you set it up this way, save the data, and then you can copy it and paste it. The noise figure values, if you have them from the noise figure mode, you can enter them from the noise figure mode. If not, you can just enter your expected values for noise figure. So that's the DUT data. So I've entered my DUT. The next thing is preamp. I am not using a preamp, so I'm going to skip this section, but it's really the same story. You can say use preamp, and if you do a preamp, you should do a user cal. You don't have to, but you really should. And then you would enter the preamp values in the preamp tab. Next, we come on down to this idea about the measurement noise standard and the calibration noise standard. Many customers use the same noise standard for measurement and for calibration for the user cal. We're not doing a user cal, but if you are, you can click that to use the same one, but it doesn't really matter in our case. For the measurement noise standard, that's the noise source I'm using. Here I'm using the 346K01. I can either just go with the default values that we have loaded. You can go with spot values where you're entering the ENR and the reflection coefficient for the hot and cold states. Or I can go with user entered. I'm doing user entered. And then I come into my measurement noise standard tab. And I enter the values for frequency, ENR, ENR uncertainty, and the reflection coefficient on and off when it's hot and cold. I got these values from the FieldFox, you get a calibration report that's sent to you, and you get a printed copy a lot of times, or you can go online and find them. And it's a document such as this. It's called the Certificate of Calibration. You can also get it from InfoLine later, and it has this data: ENR uncertainty, reflection coefficient, so forth. I essentially took this data. It took a little bit of manipulation to try to convert the PDF into Excel, but I was able to eventually do it. I think I did PDF to Word to Excel, but I copied and pasted it into there. So that's my measurement noise standard. So I have this measurement noise standard. If you want to look to make sure you don't have any typos, you can say, hey, I want to look at the ENR uncertainty to see what you've entered. Roughly looks right. You want to look at your noise source ENR. Again, anywhere from 20 to 13 dB is the ENR of this noise source. So continuing coming down on the spreadsheet, the next section is on the ENR uncertainty. So where is the ENR uncertainty coming from? It can come from a spot value. You can say it's 0.1, or from the noise source sheet. And mine is coming from the noise source sheet, which is that measurement noise standard. And then here you have to say that for this ENR uncertainty, what is the confidence level? And what's the standard deviation? If you look at the report that Keysight sends you, somewhere down here, it says the reported expanded uncertainty is the standard uncertainty multiplied by the coverage factor 2, which is approximately 95%. So we are reporting it as 2 standard deviations. And the reason you need to know that is because when we eventually combine all the uncertainties, they're combined as 1 sigma values. They can be reported as 2, 3, whatever they want, but the math, when they're combined as 1 sigma, and then they're reconverted back into 2 or 3 sigma, whatever they're reported as. I'll come back to report confidence in a minute. That's kind of the ending point. Now we come into our gamma reflection coefficient return loss. And this is for the mismatch uncertainty, which is a very big component of this measurement uncertainty. What is the noise source? What is the spec style and what is the distribution? And this I information tab is very handy because it's easy to forget. I forget. How am I picking it? And I need to pick a style of fixed because I'm using the data. Here, if you come in, you read, halfway through it says, fixed is used when the entered value is the actual value for the device. Because I'm not taking it from the spec sheet, I'm actually reading the return loss from my NA mode, I'm using fixed here. And for the distribution, I'm picking Rayleigh because while it's fixed, I've got the magnitude of the reflection coefficient, I don't have the phase. And that's why I referred to that paper earlier on Rayleigh distribution and understanding how these distributions are applied if you wanted to get more information on that. But here I pick fixed and Rayleigh for my noise source. Actually, for the gamma of the noise source, I read it from the data sheet from the noise source, and I'm not using the phase, even though I have the phase info. I'm not using the preamp, so it really doesn't matter. And then again, it's the same story for the DUT. The last part is this reported confidence. And this is really simply a matter of what do you want to report your final uncertainty as? 2 sigma or 95% is very common. You can also do 3 sigma or 1 sigma. If I do 1, let's look at this total number. This is the one that ends at 0.4, kind of. It's going to turn into about half of that if I say 1 sigma. See, now it's 0.2. It's really just a multiplier. If I do 3 sigma, it'll be 0.6. But 2 sigma or 95% is very common, so you can leave that to be as default. This is the basics of this uncertainty calculator. And here we're also showing the measured noise figure and the actual noise figure. In my example, they're about the same. They're really the same because I'm not using a user cal. If you had a preamp and a user cal, you may see a difference here, determining if you have to do a user cal or not, but we're not doing it. So that's essentially looking at the uncertainty calculator in Excel. Next, I'd like to go ahead and look at this on the instrument. So here we have an amplifier hooked up. That's our DUT with my noise source. In noise figure mode, I'm looking at noise figure on the top trace, gain on the lower trace. And I'm going to just switch this to just single trace view because the focus of this video is uncertainties, and we calculate uncertainties today for the noise figure. In this revision, we don't have it for the gain yet. So let's just look at noise figure. If you come into the noise figure mode, we have uncertainties that we could again display for noise figure, noise factor, or noise temperature. These are essentially different formats of the same thing. If you press the mesh setup key, number 4, there's a soft key called uncertainty. And you can go in there and you can turn on the different uncertainty contributions. I press uncertainty contributions, and I have user cal, which is on and off, and I'm not doing a user cal, so that one doesn't really matter. Mismatch is a large component of uncertainty. I can turn that off and look at the impact on these bars. You can see the bars will get smaller. And I think what I will do is I will zoom in. You can't see it all on the scale, but at least you can see some of it on the scale to get a sense of what happens there. So I go back to mesh setup, uncertainty, uncertainty contributions, mismatch off, and then I need for it to catch up. And you will see these bars will get smaller if I turn uncertainty off. Now let me turn it back on, and I will need to wait for the sweep to catch up. And you can see it's going up. And now you can see how much larger they are with mismatch on versus if I had mismatch off. Another component of the uncertainty is ENR. ENR is the ENR of your noise source. You pretty much, it is what you get. You may be able to send these to an IST or an MPL. I'm not sure if you still can do that to get better uncertainty, but really it's reported to you on the sheet and you put it in. But you can see what the contribution of that is. And the same for jitter. Jitter is the one that's very closely tied to your integration and how your jitter goal is set. We also have a jitter warning. Let me set an unreasonable jitter goal, let's say 0.01 dB, and say I want to do it in 0.01 millisecond, essentially 0. These little blue circles that show up say that you're not meeting your jitter goal. But the focus here is uncertainty, so I'll go back to something reasonable here. I should be able to meet my jitter goal then. Uncertainty bars can also just be turned off, or you have them back on and it shows uncertainty there. Uncertainty is one of those parameters that it will give you the right uncertainties, and it also reports it on the marker as plus and minus there, if you put in the right contributions, if you fill in the right values. If you don't fill in the right values for the DUT or the noise source, you're going to get the wrong value. So be very careful that you're giving it the correct data. Another point is the uncertainty coverage. We talked about the coverage factor. It's just a multiplier. Take a look at this bar, and if I just go to 1 sigma, this will become half of that. We may have to wait a minute for the sweep to catch up, and you can see now it's about half, or 3 sigma. But you can leave it at 2 sigma, 95%. Now, what are the uncertainty contributions? What are the factors that go into it? One is the DUT, and you can have spot values like we talked about, or you can have the actual values. And I chose to use a table here, and this is kind of one of the beauties of FieldFox, is if you go into the DUT table, you have the kind of input gamma and output gamma. But FieldFox, because it's a combo analyzer, has NA mode. And if you come and you go into NA mode, and you have your DUT hooked up, so that would be without a noise source. It would be just your DUT between port 1 and port 2. I would suggest you do a 2-port cal, you measure it. You don't even need this format change. You can just save the data as an S2P format. And then what happens is you come back into your noise figure mode. You go to mesh setup, uncertainty, DUT, edit table, and it's not recalling, but it's importing. It says import the DUT data, and here I had to save the amped data as S2P, and I can pull it in, and that fills up my table. And I want to point out that this amplifier data is in this noise figure DUT directory, so that's where it's saved. If you, in NA mode, save your S2P, let's say we save it somewhere else. I'll just call this FC. amp. This is an internal, okay? AFC-amp S2P. I come into noise figure mode, mesh setup, mesh setup, uncertainty, import. I don't see that AFC-amp because it's looking at a different directory. The easiest way is to come into the file manager and say manage files. There's AFC-amp. I say select file. I copy it, and where do you want to copy it? I want to copy it to internal. Which directory? I go into the noise figure directory because that's where it's looking for, and I say do copy. Now if I come into I'm actually in noise figure mode. If I go to mesh setup, uncertainty and I try to import the data, there I can import my data. That's the trick. You need to kind of pay attention to the directory. This is same true for ENR values. So you now have your dot values, and you want to, again, the distributions I had selected in the spreadsheet, the fixed and the Rayleigh, you want to have those here. It's really important that these are right for your uncertainty to be right. And you do the same thing for the noise source. You do mesh setup, noise source, edit recall tables. I can save a CSV on my computer, and then I can recall the CSV here, like my ENR file. The ENR format is a CSV format. And if you look at it, I said it was 2 sigma, fixed, Rayleigh, all those same parameters, and these are the values. I want to point out on the uncertainty that if you make a mistake, and let's come into the noise source, and you enter one of these gamma values, for example, a 0, meaning it's just perfect, which doesn't exist, I'm going to type in 0 at 10 gigahertz for the gamma. This uncertainty will turn into uncertainty question mark. It will do once the sweep has caught up at 10 gigahertz. Because it's suspecting, you see that you've done something wrong. We did this to prevent people from thinking they're applying the mismatch uncertainty, but not actually calculating it. If it's really easy to not have the right values in this table and have a false sense of correction. Because if you don't have the right values for the input gamma, you're going to get a really low mismatch uncertainty. So we've put this uncertainty question mark there to make you question, do you have everything right? But if you have the right value for the noise source, so let me go back here and I'll just recall the table again because I don't know what the value was that I changed. Then once the sweep is caught up, it'll go back. So that really summarizes the measurement uncertainties that you can see on a FieldFox. If you enter the correct values, then you can always have the right uncertainties and it displays it and make decisions on how you want to set up your instrument. The details of all this uncertainty, if you want more information, you want to read about it, if you go to our website, the uncertainty calculator itself, the information tab, has a lot of information, and the app note that I pointed out on Y-factor measurement accuracy also has information. So does the FieldFox user's guide. Thank you.